If nothing else, the universe is not a quiet place. There's gravitational waves. People are trying to find a way to see it. And when your clock is good enough, you will see those gravitational waves, right? And that will be the noise of your background. So that's why I feel there's no losing cause here. You develop a technology, you keep moving forward. And if one day people say, no, you can no longer make time measurement better, you have come up upon some interesting physics. Maybe quantum gravity finally will say, yeah, time is no longer continuous, it's all discrete. But that's many orders of magnitude away. By the time you see it, you will see new physics.
In this episode of the 632 nanometer podcast, Misha visits Professor Jun Ye in Boulder, where he leads the development of optical frequency atomic clocks at the Joint Institute for Laboratory Astrophysics. Throughout his career, Jun has searched for and found magic wavelengths and temperatures that enabled him to push the limits of physics. He likens JILA to Formula One for physicists racing to set performance benchmarks. Misha and Jun discuss ultra-stable cryogenic lasers, mind-bogglingly precise atomic clocks that can detect gravitational waves, and more. Please welcome Jun Ye.
So regarding the cesium atom clocks, is it correct to say that they're the most widely used these days?
That's absolutely true. And the cesium clock, in fact, is still the definition of time. The optical atomic clock, in order to be redefined as a time standard, will still take a few more years. And the reason is very simple. There's incredible technical infrastructure. All the GPS, all the satellite communications, all the country-to-country connections, and so on. It's all based on microwave standards. The optical standards is now easily 1,000 times better in terms of precision-wise, or in terms of accuracy, maybe 2 orders of magnitude better. So you can say, why don't you redefine the time now based on optical atomic clocks? Well, I must say the optical atomic clocks has been largely a research effort. And only very recently, people start to make comparisons between optical atomic clocks, between different laboratories, and eventually between different countries. It's a little bit easier to do in Europe, just because of the density of the different countries, different national labs are much higher than in the US. There's only one. Everything is in border, but also in Asia. And so these are important, where different countries need to compare their standards, because after all, it's a universally defined time. Everybody should agree, and our clocks should agree with each other. And that will take time to make these comparisons, just because we don't have readily built infrastructure to compare the optical clocks. They are much more precise than microwave clock. And so you cannot just use GPS. It wouldn't be able to do the job. You have to build fiber networks. You have to be able to maybe point lasers from point A to point B and start to demonstrate technologies. You can transfer time at a 10 to minus 18 level from one position to the other.
So are they like more expensive, or is it more difficult to scale up comparing to cesium ones? I don't know. I was just happy that, cesium atoms is already, the GPS gives us, what is it, like tens of meters resolution, and then it's like good enough for the technology.
Yeah. So you're touching on a really important point. I think it's not necessarily true optical atomic clock is more complex than the cesium clock. And oftentimes, you're pushing the very best is different from making it practical for everyone. Pushing the absolute best often involves the more complex apparatus. And I would say the very best cesium fountain clock is fairly complicated. And you have this large chamber where the atom has to be thrown up and come down. And from that perspective, optical atomic clock is actually simpler. Even though it offers much better performance. But in terms of the portability, laser is actually not very robust, right? This is the one thing what people need to make sure the lasers are robust and also small. Microwave technology is much more mature. When you say, I want to make a portable system, here's another design consideration. How much would you like to be at the state-of-the-art level versus compromising it a little bit with the good benefits of making the system much more compact, much more robust, that it can be transported and so on. And that's really is a field that's robustly ongoing right now. There's a commercialization starting to come up, In fact, I mentioned iodine clock. The iodine clock is not even cold atom based. It's just relying on vapor cells of iodine. And the reason why that they are selling commercially now is because they're offering something that's potentially better or at least equal with a maser, but it was a performance, but it was much smaller footprint. So that started to become really useful. And also when you talk about how useful is a clock, that question really has multi layers. You can say, I want to have a clock to eventually be able to see space-time ripples, eventually be connect on how quantum physics is being influenced by gravity. I do believe as we continue to push on this, we'll be able to start to explore these very fundamental sectors of space-time and how quantum physics and gravity is connected. Because you have to make measurements to be able to, you cannot just rely on mathematician to come up with these different kind of string theories. You have to explore, right? And the clock is one of the best tools to explore. And you never know what you can do when you go down to the clock at 10^30, what are you going to find out? So this is what drives me the most in terms of really pushing that frontier. And one of the experiments we recently published was, okay, I can move my clock by a couple hundred microns, essentially on the scale of a human hair, or maybe a little bit bigger than a single human hair. And you can start to see time is different because of Einstein's general relativity. And what if we pushing that by another factor of 100, then you will start to see, time is different on one de Broglie wavelength of your atom. So how do you write down this Schrödinger's equation when you have psi xt, but x determines what time t is, depending on the local gravitational field. And stuff like this would allow you to start to see, okay, how the quantum coherence, vertically positioned quantum system might look different from horizontally positioned quantum systems. It's not a quantum gravity, that would take a much more decades to go down to see things. But when you want to start to make those connections, that requires much better clocks than we currently have. But then you mentioned GPS. GPS is an incredible technology, right? Everybody relies on. But if you say, well, what if our civilization is not just satisfied being confined on Earth? What if we want to make the whole solar system to be livable place for the human civilization? I think sooner or later it has to happen. We cannot have just one home. So if that happens, maybe you want to have a GPS for the whole solar system. And just because of distance so expensive out there,
huge delay on getting the signal.
The GPS may not be good enough. So you need it to be really accurate, because by the time I'm about to land on Mars, you're off by 10 meters. That signal takes a very long time. You have to be self-guided. And so from that perspective, I would say, I know there's a lot of a military aspect of time, and I'm not really into that kind of stuff. But it's really important also, if you say, I have a vehicle and its GPS is gone, and that vehicle is flying to reach a certain distance, well, you have to rely on your own clock on that vehicle. So, and the cesium clock wouldn't be good enough.
And currently, for those kind of interplanetary trips, like let's say what is sent like to Mars, the rovers, so they have like on the rocket, on the spacecraft, they have the clock. So is that the way it works right now with like cesium clock? On board?
those are all microwave technology based, right? But I do think in the next coming decades and so on, I think you will start to see lasers in space. I mentioned I have some dream about our silicon cavity should be sitting on the surface of the moon. That's because there's a permanent shadow area where the temperature is very stable and the vacuum is already good on its own, and all these things, and there's no seismic noise unless we hear alien footsteps. And so if all of that is true, you start to build optical networks up there, and for deep space navigation and so on, would it be much more efficient with the laser beams and stuff, microwaves and so on. So
sounds like a great moonshot.
Yeah, the precision is much higher, and people are already talking about putting gravitational detector in space, like LISA project. And that's already requiring lasers to be able to track. If you can get the laser downstairs to be able to engineer it and package it up to go to satellites, we will be able to see satellites millions of kilometers apart from each other, and it can connect them coherently. That means the distance between them won't be wrong by a small fraction of the laser wavelengths, picometers, out of millions of kilometers. And if that comes true, you can look much further into deep space, because now you can think of your aperture of your optical interferometer is a millions of a kilometer distance. Now you maybe see the final edge of the universe,
Wow.
because you can synthesize the aperture.
So maybe if we could expand a little bit on, like, for those who are new to the field, what the person should know who is like getting into the field of high precision measurements, atomic clocks. So what are those, like, maybe concepts or methods which are typically used? And
Yeah. And in some sense, you will say, okay, molecular spectroscopy with laser, that's really not, in the late 90s, that's no longer at the forefront. Laser spectroscopy in the 70s, 80s was moving forward tremendously. But in the late 80s and 90s, people were already talking about quantum information, ultra cold atoms. After all, Bose-Einstein condensate was created in 1995 when I was a graduate student here in this institute. So there's other really vibrant fields are starting to come up in AMO. And I was working on molecular spectroscopy, in some sense, a little bit of a traditional spectroscopy techniques. But this goes really well with the question you just asked. Seemingly, I could easily just be doing spectroscopy all my life, and how did that? I moved from doing that kind of a molecular spectroscopy into building some of the best optical atomic clocks that's out there, really connecting quantum metrology to the frontiers, connecting to quantum information science. I think it really lies in the spirit of JILA. Like, I was doing this molecular spectroscopy, but I learned a tremendous amount of laser frequency stabilization, control of optical frequency. How do you utilize a very high finesse optical cavities that you can store information there, you can later retrieve it at will? How do you later on learn to lower the temperature of molecules such that when you do precision spectroscopy, you can always chase for better spectroscopy resolution, coherence time, systematic effects? And these are just, a simple term of spectroscopy actually contains all of that ingredients. And so it was very powerful when I decided to pursue postdoc with Jeff Kimball at Caltech. There, specifically, I would like to learn was still using optical cavities, but getting into the quantum regime where this interaction between atom, molecule, and a cavity is so strong that you can no longer consider cavity as a perturbative thing, as allow you to enhance the signal to noise ratio, but itself turns into a quantum object. The coupling between atom and cavity is no longer separable. And it turns out, as long as you keep your eyes open, to keep your mind open, and pursuing new knowledge, understanding what is interesting physics can come out of it, with some very basic state-of-the-art technical advancement training that you have, you can do a lot more. So suddenly, when I was at Caltech, I feel like, oh, I know how to put atoms in the cavity. That's what a cavity QED Jeff Kimball was pursuing. But I want those atoms to stay there in the cavity for a long time. So I better learn about laser cooling and trapping. I better get into ultra-cold atoms. I better get into optical trapping of atoms. Once the atom temperature is low, I want to hold them in front of me so I can have a long coherence time. And these atoms, maybe one can give you some bits of information, but maybe that's not enough. Maybe you want to have tens of thousands of atoms, or maybe millions of atoms. So you can see this from traditional spectroscopy suddenly went into this quantum regime of strong coupling, but then moved on to manipulating and state engineering of quantum many-body physics systems, such that you can turn this into a much better spectroscopy or precision measurement platform. And so I really credit my PhD and a postdoc, the working experience with these intellectual giants that allowed me to open my eyes to connect these seemingly different fields, right? And that's now all connected, and they all become basic ingredients in building an atomic clock.
All right. So then moving to atomic clock. So what is, if you could explain what are the necessary ingredients for atomic clock
Yeah.
and how to measure time with atoms and lasers and
Yes, perfect. And I mean, in some sense, the essence of an optical atomic clock, why I say optical atomic clock instead of just atomic clock. In some sense, atomic clock is what we are trying to understand when electrons moving around nucleus. It has certain energy scale associated with it. If you put it, whether it's electron spin or whether it's actual orbital motion around the nucleus, how well you can put in a field into the atom, and that field will interact with the atom and cause the electron to either spin flip or jump its orbit from one orbital motion to another. And you have the specific energy that's associated with this particular excitation process you're happening. And this process can be in the microwave. That's what a traditional cesium clock is all about. You're shining 9.2 gigahertz microwave signal onto a cesium atom, and you can spin flip the electron. And once you hit that resonance, you can lock your microwave signal onto that atomic resonance, and you say, aha, now I have created an atomic clock because my microwave frequency is now connected, or the traditional word is called slaved, but I don't want to really, it's being servoed onto the quantum resonance. And so you can see immediately, you can see two important ingredients. One is you have to have a very good microwave oscillator. And the second is the atom, which is going to serve as a reference, has to be free of perturbation as much as possible. Such that, I need a good microwave oscillator because then I can move
is it the maser?
Yeah, it can be maser, and actually, in fact, in the modern, the microwave atomic clocks, even the maser stability is not good enough. People actually look for cryogenic sapphire oscillators and so on. So there's a very strong connection. Later on, I'm going to talk about optical, but I want to start with microwave first.
So maybe coming back to like a little bit of history of the atomic clocks. So was it, as I understand, it's primarily like the field started like from Ramsey or maybe just to
maybe even Rabi.
Yeah,
I think really Rabi was the first one, I believe, that proposed right after World War II. You have a natural transition in those atoms. They should be serving as our timekeeper. And it's just amazing idea in some sense that he's just absolutely right, is ahead of his time, of course. But that's how the whole field started, basically relying on the fact the natural resonance that's happening in a quantum system like atom or molecule, and you're trying to use this instead of artifacts that we make. Okay, here's a little pendulum and it's swinging under the gravity, but that depends. The frequency depends on how long you made the string and so on. Those are artifacts, right? So the clock should be made out of natural phenomena. And if you have an atom, that atom, whether it's in any place on the surface of the Earth, if you have done your experiments right, they should all tell you the same frequency as long as you know your geopotential. So that's the basic idea. And the Ramsey contribution came from, he came up with this so-called a separate field, oscillatory fields idea, where essentially like you and I want to check our time. We'll compare our time now, and then we go out to have lunch, and we come back and we check our clocks again, and we'll say whose clock is moving faster and slower. The Ramsey idea basically allow you to use microwave to set the spin in motion. And you wait a certain time, and you come back and see whether the phase or the frequency of the microwave signal and the atomic evolution has walked off from each other. And you can use that information to make a correction to your microwave. And that's what I mean when I say microwave is now servoed to the atomic resonance. What you're doing is basically comparing the free evolution of the atom against the free evolution of the microwave source, and make sure they are connected.
I see. So why at that time it started from like radio frequency range, like microwaves? Is it because the sources were much better than using, let's say, like same for optical transitions?
Yeah, so from historical perspective, this is only natural. In World War II, that's where radar technology got it matured. And so microwave technology is just pervasively used in the modern societies in the 50s, 60s. And so it's just very natural. You're looking at the microwave transitions in atoms. Laser wasn't even invented.
Yeah, it's like later.
So the laser was invented in the in the early 60s. It's a kind of interesting. This is exactly the generation of my thesis advisor, Jan Hall. They were young at the time, and then when laser was invented by people like Charlie Towns and so on.
Basov Prokhorov.
Yeah, exactly, from the Soviet Union,
Soviet
and
Union,
yeah, and Basov and so on. Yeah, and the idea of, oh, maybe we can actually use these optical oscillations to just build as a clock, just like a microwave. Those ideas were early on unthinkable because the optical frequency is so much higher than microwave frequency. We're talking about million times higher. There's just simply no electronics that would allow you to count the oscillation of the light. And so people don't think about using optical clocks at the early days of laser development. But I have to say, people like Jan Ho and so on were involved in measuring speed of the light. There, you can already see, in order to determine the speed of the light, you need to measure the wavelength and you need to measure the frequency. Because lambda times f equals to c, speed of light. So if you can somehow do very precision metrology to measure the wavelength of a particular laser, and you also can measure the frequency of that laser, then automatically you have the most precise measurement of the speed of light, c. Mm-hmm. In the 1970s, this is still the frontiers of science, like speed of light. What is that value? How can we define it? Or later on, in fact, speed of light is now the constant of nature that's being defined as a particular value. And that triggered some of the early interest of developing so-called frequency chain to be able to go from microwave step by step all the way up to the optical frequencies. So you can measure optical frequencies through many intermediate mid-IR lasers and so on to build this gigantic chain to be able to measure those frequencies. And once that idea was realized, people start to dream. Okay, then it must be possible that we can use optical transition directly to make a clock. But you can still see it's a non-trivial. This chain is many looms full, operated by several PhDs. But why optical would it be attractive? That's actually very simple. If you have an oscillation that's 1 million times faster, but lasts the same amount of coherence time, meaning, suppose in 1 second is your coherence time, microwave oscillates or 10 gigahertz, meaning you have 10 billion oscillations per second. But optical, you can have 1 million billion oscillations per second. And obviously, if you can keep track of all these oscillations, the one that's oscillating faster will allow you to accumulate less mistake. And so that's the key thing, is optical transition offers a better quality factor. Or another way of saying, in a given interval of coherent evolution, you have accumulated more sinusoidal pendulum type of oscillations, so that fractionally speaking, the mistake you're making is much less than compared to the microwave. That's the key. But you can see, just like a microwave oscillator, you have to make a laser to be really coherent. So now we are talking about pushing laser frequency stabilization to the state of the art and go much beyond compared to the 1990s and 2000s. The other is that the atoms now are going to be providing the reference, not in the microwave domain, but in the optical domain. And we all know about Doppler effects. So when the wavelength gets much shorter, the Doppler effect gets much bigger, fractionally speaking. The Doppler effect is proportional to the so-called k vector, 2 pi over lambda times the velocity. When lambda gets really tiny, any little motion provides a sufficient frequency shift that you have to account for. So suddenly, in microwave, maybe the atom motion can still be tolerable. In optical domain, any little motion, a centimeter per second kind of a motion leads to a very significant frequency shift. So suddenly the laser cooling and trapping and cold atoms becomes the centerpiece of research for being able to develop optical atomic clocks. And so you can see where all these small pieces are coming together: laser frequency stabilization, control of ultra cold atoms, engineer many body states. You want to put as many atoms as possible together so you can get a higher signal to noise ratio, and they all have to work together. And then finally, now you have this one optical frequency, say, servoed onto the optical transition atom. You still have to translate that frequency down to microwave. And these days, we do not use this frequency chain that I described earlier, but we use optical frequency comb. This frequency comb is a concept actually a Russian scientist, Chabatayev, came up with in the 1970s. At the same time, completely independently, a young professor, Ted Hensch, at Stanford University, came up with these ideas. And so these ideas were very early on, but it did not get realized until 20 years later when Ted Hensch's lab in Munich, Garching, was really able to start to demonstrate the frequency intervals can be bridged by model lock lasers. And then Jan Hall, has been working on optical frequency entire life, and he was considering retirement at the time. But then the optical frequency comb generation, this revolution really hit us. And Jan's, of course, has all the tools in his up his sleeves of how do you laser frequency stabilization, how do you broaden the spectrum of the model lock laser further so they can do in one step connecting pulse trains to actual frequency comb to stabilize it. And that idea, and I would say super happy for Jan Hall and Ted Hensch shared the Nobel Prize in 2005 for that development, because it's a revolutionary. It suddenly allow us to have a single oscillator in the optical domain to be connected to the microwave with a very small device. You no longer need a room full of lasers with 10 PhD operating it. Just one graduate student does it all. So this just opens up tremendous amount of the research possibilities. And this is the one area where oftentimes a fundamental research piece, like I want to build optical atomic clock, I need to be able to count the optical frequency. Well, the frequency comb allow you to do that. But actually frequency comb offers much more. Suddenly now we are using frequency combs to do sensing, because a comb can have essentially the name of comb implies that you can have many zillions, millions of optical markers. They are all phase locked together over a very broad optical spectrum. And these days we are pushing into the infrared, the extreme ultraviolet. And in the infrared, you can use the frequency combs to measure molecular resonances. And we are using this now to measure people's breath, to understand if you get sick by COVID or maybe have a lung disease and so on, your breath will change. And we will be able to use a frequency comb to measure the minute amount of changes of molecules coming out of your breath to tell you what to be watching for, what are possible problems with physiological conditions of your health. And this is kind of amazing, right? This is a research tool, had nothing to do with biology and medical science. It was really meant to be serving a very specific goal of connecting optical frequency to the microwave, and yet it's just tremendous amount of application.
So was it the original idea of the comb? Was it's like a gear cog between the optical frequencies and the microwave, so you can?
It's like a reduction gear. It's like if you're the avid biker, and this is exactly the idea. Like you're going up the mountain or going down the mountain, you want to go to the low gear and the high gear. And what you are doing is, of course, it's connecting the two front and back wheels with this reduction of the gear things. But it's really important, this gear connection. Every single tooth matters. You cannot have one of them just miss a few tooth. That system won't work. So this optical frequency comb connects the two rotating wheel. One is in the microwave, the other one is in optical. And of course, just imagine this wheels are optical frequency is 1 million times higher. So it's like you're riding a bicycle in city of Boulder. this bike is gigantic. The other one of your wheel is this small, tiny, regular one, but the other wheel is as big as the radius from Denver to Boulder, and you have to somehow have a chain to connect them up, and this connection has to be completely phase coherent. In another way of saying, every single little click on the gear is translated into our distance.
So, Jun, so you are a fellow at JILA, and I'm sure not that many people know about this place, and it seems a special place for like science and technology. Could you tell a little bit more of what is this place?
JILA was founded in 1962 as a joint collaboration between National Institute of Standards and Technology. At the time, it's called the National Bureau of Standards, and the University of Colorado. The goal was to create an open scientific research environment with support from both U.S. government, federal government, such as NIST, as well as academic institutions like the university campus. And it's been incredibly successful because of this collaboration. And on one hand, you have stable funding sources to pursue the best of science that can be connected to, say, Commerce Department or NIST's goal of pushing the frontiers of a measurement science. What's the core of setting up standards of physical sciences? And at the same time, open-ended research, pursuing intellectual frontiers of physical sciences in an environment which is academic institution. So this combination of both some seemingly mission-related research, on the other hand, completely open-ended research, just explore the background, the nature, and the fundamental science, and with a combination of a technology development and the accumulation of knowledge. That's been really the secret sauce of JILA's success, where you can develop your own tools, develop your own technologies, train the best students, and pursue the best science.
I would also add that the JILA architects, they put some thoughts about the views, so make sure that the scientists enjoy the best views of the Rocky Mountains. So while we were working along the hallways, I've seen there was the doors or the offices of like several Nobel laureates. There was like Eric Cornell, John Hall, Carl Wieman, and probably like many others. So how does it feel to be in such a condensed state working with those people?
Well, in some sense, it's humbling. Of course, you're working with giants amongst yourselves. On the other hand, it also feels very natural. These are the people we work day in and day out. And I was a PhD student of Jan Hall, and and I have been collaborating quite closely with Eric Cornell over the past 15 years, working on the search for the electron-electrical dipole moment. And as you're working together and pursuing what's the next circuits to build, what is the next laser to control, and what's the new physics ideas that's underlying some of the best experimental protocols that we are coming up with. You don't view them as, oh, these are incredibly intellectual giants, and so you work them as just your coworkers, just people they can get ideas from, people who you can have intellectual debate, people you can check your ideas against with, and it just feels very powerful in that way. You have, after all, people who are really interested in pushing science and technology forward, and they are just simply your colleagues. You're working with them closely. And I think this brings the best out of everyone. And I think where I work with my students in a very similar spirit, I always say, I'm one of you. I'm one of the students who are learning together about things. And so I might come up with many ideas, and I know 99% of them are wrong. I'm just challenging everyone, each other, and during this kind of discussions and debate and pushing on each other to do the very best, we can oftentimes indeed find a creative solutions and creative technologies and do best science.
And according to like your biography, so you first joined JILA for your PhD work with
Yes.
with Jan Hall. So I guess at that time he was not yet as famous. I don't know. He was not yet a Nobel laureate. Was it 2005? So what brought you here? Like, how did you end up in such an amazing place?
Yes, that's an excellent point. I certainly, when I was a young student, never thought about these kind of a prize and awards and a prestige or famousness. But I did hear about Jan's name when I was working. At the time, I was actually a student in New Mexico, University of New Mexico. I was working with a scientist working on diode lasers. But at the same time, I was very interested in quantum optics theory. And there's a fellow down there called Marlon Scully, who, in fact, is one of the true pioneers of establishing when the laser was invented. Scully, Lamb, and Sargent came up with one school of how do you use quantum optics to really explain how the laser working principles of lasers. And I read all his books that he wrote and talked with him. I wanted to work as a theory student with Marlon at the time. But the Marlon was moving towards wanting to build some experiment. And I was like, who are the best experimentalists who realize these fancy, incredible quantum optics ideas? And to me, as a young person at the time, those was just incredibly romantic. These annihilation operators, and it actually can be realized in the laboratory, demonstrating photons flying around. You can think about entanglement. You can think about coherence being correlated, that you can see how the line width can be beaten down because of the coherent evolution of the multiple quantum states. It was just very eye-opening to me. And at the time, I really felt, I'm learning a lot of theory from Marlon. I'm learning some technical things on semiconductor lasers. But I want to find the very best technical person in pushing the experimental science, especially related to the lasers, forward. And through the discussion with my fellow professors at the time in New Mexico, in Los Alamos, and then was lucky enough, Marlon sent me to a conference in Snowbird, one of those winter conference of quantum optics. And there I met Jan Hall.
What is it? Is it a PQE?
Yeah, it's a PQE. And it's always right after January 1st. And Marlon took a bunch of his research groups to that PQE meeting. And there I met Jan Hall, and he was there giving a talk about laser control, how to build most stable interferometers so that you can stabilize optical frequencies. I just find that fascinating. At the time, I have to say, my experimental knowledge is still very limited, but I can find this very strong connections. Yeah, if you can do this type of precision stabilization of laser frequencies, you must be able to open up many different avenues to pursue quantum optics. So I decided I want to work for Jan at that point, and I approached him, said, can I transfer from New Mexico and come to Colorado to be a student? And Jan gave me a cryptic response.
You already studied your grad school in New Mexico?
In New Mexico with Marlon Scully and with John McInerney, who was a professor in electrical engineering working on semiconductor lasers. And I decided to transfer here, partly also because Marlon was also considering moving from New Mexico to Texas A&M. And so I identified Jan to be a place where I want to really pursue my PhD in experimental physics, experimental AMO physics. And Jan I remember he welcomed me. He did not hesitate. He said, yeah, if you really want to come, you look like a brave boy. If you really want to come, you're welcome. And I didn't realize what that means. Actually, later on, I found out the reason why Jan says, oh, you have to be a brave boy to come work with me is because Jan just let people, in some sense, pursuing their own dreams in his laboratory. And some students may take 10 years to graduate. And in my case, actually did not take me that long to graduate. But nevertheless, that was a good sort of a Jan Hall speech.
Was there a special requirement? Because I know each professor has its own views on what the students should accomplish to receive a PhD.
Indeed. I have my own view of what each of my group should accomplish.
So what is it?
In my group, for example, I often feel that it's not about number of papers you have published. It's not about how many invited talks you have given, but it really towards the end of your PhD, the student should be the one who leads an intellectual front of developing a particular experiment. He or she should be the leader, and he or she should set up the agenda, saying, "Hey, I just read a few different papers, and that's what the connection I can make with what's the modern context of the field is moving forward. And here's what I can contribute uniquely with my experiment. Why don't we do this?" And this person starts to inspire us, starts to lead the development, start to design the experiment, design the protocols of a measurement, eventually write a paper. Then I think this student is ready to graduate because he or she is now a team leader, and he can design ideas and can come up with new ideas, can design experimental sequence to fulfill or realize what she or she's thought being interesting.
So the student needs to propose what kind of experiment to accomplish, and then this experiment needs to be
working,
move forward
yes,
the state of the art.
Yeah, that's correct. I mean, when I say proposing, of course, it's not coming out of nowhere. In laboratories like ours, it builds on previous generations of students' work, and as you're growing up within the group, you're talking with your more senior students and your postdocs, and you have some ideas what you're doing, but nevertheless, you cannot just repeat what's been going on, right? You always have to come up with your own idea of, I'm going to pushing this particular apparatus, this particular experiment. It's been great doing experiment A, but I'm going to do experiment B that is cutting new corners or opening new doors, and that's when I feel the student is intellectually mature to graduate. And in coming back to my advisor, Jan Hall, I felt, in some ways, Jan never gave us a specific deadline, like you have to do this, you have to do that to graduate. It was kind of left to your own, a little free-ranging a little bit in his lab. And his group at the time when I joined is very tiny, just a few students, a couple students, I remember 3 or 4. And we each had our own project, and we were just doing our own things. But it was tremendously useful because we get to talk to Jan very often. When he's not traveling, we can go to his office all the time and talk to him. So, and this kind of a close connection between us, advisor and student, is something I really believe in. My group is in fact a lot larger than Jan's at the time, but I maintain that spirit of being very closely connected to each of my students.
See, each of them is a gem or like special talent.
Exactly. Yeah.
So when at that time, when during your PhD, so what was like the main contribution or results you have achieved during that period?
So I was working on a molecular spectroscopy project, and actually worked on several. One is, for example, iodine spectroscopy, using iodine molecules to establish optical frequency standard, and that's actually being commercialized right now. After 25 years or so, there's a company who's selling iodine-based clocks, and that company was part of that company was founded by my former student. So you can see this intellectual lineage. And on the other hand, I was also working on molecules where you can look at the vibrational transitions and so on. You can also look at the overtones of a vibrational transitions, meaning the molecule like to vibrate, but if the vibration is never harmonic. And so there's a higher order transition states that's available. It's called overtones in molecular spectroscopy. The overtones are much weaker than the fundamental vibrational transitions. And so we had to develop some very sensitive molecular spectroscopy techniques by, for example, putting molecules inside an optical cavity to enhance the path length interrogation. And you have to lock your laser to the cavity with high precision. Even doing so, you still have noise. Cavity can convert laser frequency noise into density noise. And you have to come up with some clever tricks to remove the noise. Another way of saying, you're trying to enjoy the benefit of the optical cavity without suffering from the side effects. And oftentimes when you enjoy the resonance buildup, you also have to sacrifice some noise performance, but we do not have to.
So speaking of laser stabilization, what's like maybe from technical like criteria? Is it like frequency diffusion, or what what do you try to control, and how is it done with the frequency comps?
I mean, in some sense, so you're asking a question about, maybe we'll talk about single oscillator first before you
Sure.
span up to the entire frequency comb. So if you have an oscillator, the oscillator spits out sinusoidal wave, but we all know that sinusoidal wave can never be completely stable. It's got a little wobbly on its frequency, no matter how you look at it. That frequency fluctuation can be looked at on its Fourier spectrum, and you will see at the different parts of the Fourier frequencies, it has different power spectral density of noise.
So what usually causes the noise, like to shift the frequency?
Can be many reasons. So for example, I have a laser, and the lasers are basically defined as a frequency running between two pieces of mirrors. And as I speak, I'm vibrating the air a little bit, and those two mirrors will be vibrating, and that would already cause perturbations. But even if everything's held in steady state, the very fact that this oscillator, these two mirrors, are not in absolute zero temperature. Mirrors are made out of mechanical devices, mechanical material, and any mechanical systems will have dissipations. We all know that. And Einstein, long time ago, wrote the so-called dissipation fluctuation theorem, that anything that has dissipation, meaning you have a constant kT worth of energies being fed into each degrees of freedom. That's the thermal equilibrium concept. And so with the dissipation just means there's always a fluctuation of each mechanical modes of that mechanical system. And all these mechanical modes are working independently because they're being fed by thermal energy. And that means each mechanical mode is fluctuating in some ways independent of the other mechanical modes. By the time you sum up all the mechanical modes, the position of your mechanical system is fluctuating. And that fluctuation is completely obeying the Brownian principle that it's proportional to the temperature, and it's proportional to how lossy the mechanical system is. And so if you just have a pair of mirrors, suppose you say, I'm putting in a place where there's absolutely no vibration. Let's say we put on the surface of the moon. And actually, I've been thinking about how do we build the most stable laser on the surface of the moon. That's why I'm mentioning this. Yeah. and because the temperature is also very stable there in certain places. And you have the temperature servo, you have done a really amazing job. There's no temperature fluctuation, because otherwise thermal expansion would be another noise. So suppose your temperature, you have done a good job, your temperature is very stable. You still have this very fundamental noise that you can never overcome, unless you cool everything to T equal to 0, but then we wouldn't be here. So that is the so-called thermal Brownian noise of a mechanical oscillator. And that's limiting all the noise of the best precision metrology interferometers. LIGO is a perfect example. LIGO, if you talk to the LIGO scientists, they will say, yeah, the mirror thermal noise contributes to this lower bound that we can have in terms of the detectable gravitational wave. So it's kind of amazing, right? The little optical technology is what's limiting how far we can see the universe, how these black holes are emerging and spiraling along each other.
So is it the LIGO team succeeded like the most in terms of making those mirrors as stable as possible?
They make those mirrors as stable. They make mirrors really large so that the optical field is very large. They can average away some of the mechanical motion by smoothing over across a large surface area. And they are LIGO people actually are talking with us together in terms of solving. For me, I want to make more stable lasers. For LIGO, they want to make more stable interferometers. And they are the same thing. And it's just different scale of technology. And so from that perspective, it's a good question. Just trying to make a more stable laser turns out has a gigantic connections to different areas of science: material science, optical coatings, how do you grind the mirrors, what kind of mirrors you make, how do you attach the mirrors to your interferometer, how do you hang the interferometer, how do you suspend it, and so on. And that alone is an intellectually quite rich field. But for us, for making atomic clocks, that's just one ingredient, right? You have to make the laser extremely stable, such that you can enjoy long coherence. The best record now we have is we can have a laser have a coherence times of 10 seconds and beyond. And that means I can be speaking the sentence with you, and my oscillator is still phase coherent by the time I finish my sentence. And so only with tools like this, which can really push advance the frontiers by when I put my atom in coherence position, it's going to have a long quantum coherence. And I want to be able to match my optical coherence of the laser with the quantum coherence that's being offered by the atom. So they can really have good time talking to each other, all phase coherent.
So if there is a task, let's say, to make the most stable laser, so you mentioned one way is to build it on the moon, but if it's done somewhere here on Earth, would it be just try to use like the same LIGO infrastructure instead of maybe Michelson interferometer, like build just to mirror cavity?
Yeah. Yes. So even on this, there's a variety of different ideas. LIGO, of course, is building a very gigantic interferometer, and that's for them. They needed the path length to be really large because you want to be sensitive to the wavelength of the gravitational wave. So if it's too small, then the fractional fluctuation, or the fractional change when the gravitational wave hits you, it won't be as sensitive, right? So for LIGO, they want to build it very large cavities from that perspective. And their cavity does not have tremendous finesse. For them, it's factor of 100 and so on. The length is already large enough. And if the line width becomes really, really narrow to lock on if the finesse is high. For us, building optical standards, optical reference, I actually wanted my cavity to be there. I'm not here to detect gravitational wave for that cavity. The cavity is trying to build as long optical coherence time as possible. So you want to build a cavity which is mechanically very stiff. And the two mirrors, you do not want them to be vibrating against each other as much as you can. So you want to be isolated from the mechanical perturbations of the environment. You want to temperature stabilize as much as you can. But the one thing we share with LIGO in common is coating material that we use for these two pieces of mirror has to be extremely low mechanical loss and well controlled, well understood what is setting us the limit. And in fact, all the best stable lasers sitting downstairs right now is limited by the thermal noise of this process that I was describing to you. That's directly proportional to the temperature. And so that alone is to make, for example, right now in our group, we work with the silicon cavities. And this is actually a collaboration project between my group and the PTB in Germany, that German standards laboratory, that we use pure silicon material and cool down to certain temperatures where the silicon itself no longer has thermal expansion coefficient. And we then attach two very high mechanical purity mirrors to it, and with a good coating where the thermal noise is mitigated to the fundamental level. And that provides us with the best stability at the moment of any laser. And then we use this to stabilize onto our strontium atoms and other things. Using frequency comb, you can actually transfer the stability from one color to all the other spectrum. And that's another powerfulness of a frequency comb, that I can just make one stable laser and everybody else can enjoy it. In fact, our one stable laser right now through the fiber network, through frequency combs, is being enjoyed by our colleagues at NIST, as being enjoyed by several different groups within JILA. So it's almost like we got this ultra pure optical fields, and you open your little water tab and the optical fields coming out, and it's a very stable laser. I have heard from my colleagues from both MIT and Harvard, my best friends, Michel Lukin and Vladan Vuletic, has often said, Jun, we should have a fiber from border to Boston so that we can just open up and enjoy your stable lasers. And that's really true. This is a really amazing kind of a technology that's coming up. But on the other hand, you were asking what's the ultimate laser? You always have this mechanical loss. maybe ultimately what you want to do is having the coherence being generated directly by atoms. So perhaps what we want to have is a so-called optical maser, where you put atoms in between the two cavity mirrors. And those atoms are super narrow, just like my strontium atom. It's extremely long coherence time. What if we have these atoms to sort of store the information of coherence in it?
So would they serve as like active media? in some
Yeah,
sense?
so now it becomes like active media, but it's not a traditional laser. In traditional laser, the gain bandwidth of the active media is often broader than the Fabry-Perot cavity line width.
Yep.
But here we are reversing that role. We actually make the laser line width to be even narrower than the cavity.
Interesting.
So this serves a purpose where the laser memory, the phase coherent memory, is not being served by the atom itself, but not the cavity is providing a feedback, is providing the photon to go back and forth to connect all these atoms.
So how narrow can you go with the atomic
So
transition?
for sure, we should be able to go to. So at the moment, just for the speaking, just at today, my strontium atom, we can go downstairs and actually have these atoms be phase coherent for a few minutes, 2 minutes. I prepare them in coherent superposition, and they will be staying there for a couple minutes. That's quite amazing. My laser is not quite good enough. My laser can be, I put them in coherent. I put them into a coherent state, and the phase coherence can be about 10, 15 seconds, but not quite a minute
Like
yet.
minutes.
So in principle, if I'm using strontium atom as my active medium, I can in principle pushing the coherence to at least to the strontium level. There are some theories out there, and we can be tested, that if you use a collective effects, where you say you have 1 million atoms in there, some of the atoms are decohering away. Some you can continuously put more atoms into the system. Suppose you make this into a continuously available pumped source. The collectiveness of the photon interacting with all these atoms will make this quantum coherence more robust than individual atoms' decoherence, because spontaneous emission is connected to the individual atoms decaying away. But if you have this gigantic coherence that's living there defined by the collection of all these atoms, potentially we can push in the coherence time beyond individual atoms' spontaneous emission time.
So what's the way to measure coherence at this really long time? So you mentioned earlier, like let's say with atoms, like
The Ramsey spectroscopy.
and then
Yeah, exactly.
you kind of
That's how we do it.
let the atoms evolve, and then you
Yeah.
come later
Yes.
in a minute and then check whether they're
Yeah.
in the same state or not. So does it? How does it work? Like for lasers, what's the way to measure their coherence?
So one is using atoms as their reference. So we can tune atoms. You're asking some questions which is very much at the forefront of our research, right? You can use atoms as your spectrum analyzer. Your atom is a little qubit, and your laser come in, and you can ask a laser to rotate that qubit, and then you can check after 1,000 rotations. You can check how well the laser has done its job. And this is called a fidelity. We can connect this to quantum information, quantum computer. And you can also rotate it a couple of times and then take a rest. The things are evolving, coherent evolving. And after a certain time, you come back and check it again. And all these things can allow you to tease out what kind of a frequency noise you have in what Fourier spectrum of the laser itself. And that's one way of doing it. You can
For running this kind of atomic transitions, it kind of depends on like several things, right? It's like also intensity involved, and then
yes, absolutely.
the pulse duration. So you
Yeah.
have other parameters which
you can do things like, okay, I'm doing pi pulse, I'm doing pi over 2 pulse. These are connected. The so-called pulse area is defined by the electric field multiplied by the pulse duration. And pi just means that the dipole moment associated with the two-level system multiplied by the electrical field multiplied by the pulse duration equals to exactly pi, meaning that when the atom is pointing down a ground state, it will be flipped into the excited state. But you can do pi over 2, meaning you're in coherent superposition. But what you may be asking is, how do you know you're doing exactly pi over 2? There will be
Right.
mistake on it. And so, but there's techniques. You can say, oh, if there's a problems, I can ask it to rotate pi over 2, but I don't really know. And so what I can do is ask the rotate up and rotate down, rotate up, rotate down. And or I can keep asking rotate up and rotate up. And those two different techniques will allow you to know how much noise you actually have in your system. So there's all kinds of ways to check what's the amplitude noise, what's the phase noise. These are two different quadratures of the electromagnetic field. The sinusoidal wave that we described earlier can have both amplitude noise and phase noise. And we can figure both of those out. These are just two quadratures of this electromagnetic field.
So just like maybe to summarize, like for lasers, so one thing is the central frequency, how much it shifts.
Yeah.
And the other thing is how broad is that the frequency kind of distribution. So
that's actually the same thing.
Same thing?
Yeah, that's why I was trying to say, if you have an electromagnetic field, right, you can ask yourself to do autocorrelation function. You can say, I'm going to delay my field by a certain time, and I correlate it with field with original duration. And by varying the delay time, you can figure out how the noise is really changing. So what you were describing of, I have a slow motion of the central carrier, and I also have a line width. If you think about it, it's just a continuous language to describe how the laser frequency noise have a Fourier distribution. The low frequency end of it is dictating how much the frequency is moving around. So for example, when we're talking about thermal noise, it has a so-called 1/f spectrum, meaning the frequency noise comes down as a 1/f. Which means the center frequency is doing this diffusion process. But on the other hand, this 1/f noise will meet up with so-called a flicker floor, with a shot noise. How well you can measure certain things is limited by how many photons you have in your system. And that provides another limit on the noise process, and that's white. So 1/f noise will meet up with the white, the photon shot noise, and sometimes you have a mechanical resonance sitting on top of those backgrounds, and so you put them all together. You can integrate from a Fourier frequency from very far above your bandwidth all the way down to the frequency where you say, I have accumulated enough phase excursion that is now the sinusoidal field. I can no longer define myself to be in this particular cycle or the next cycle because there's enough phase excursion of a pi radian has occurred. And that would be the definition of what is a coherent line width. And so you see what I'm saying? You have this coherent oscillation. You can say, I have a delta function, and this delta function is moving around. But of course, nothing is like the black and the white. The delta function is never a delta function. Like as you come closer and closer to the carrier, you can start to see there's a phase noise rising up. Just like the Rocky Mountain, takes a little slope to go up.
Not perfectly steep.
Yeah, not perfectly steep. And it's because of that, it's related to the fact, because it's not perfectly steep, it's also connected to the fact that there's a center frequency is not perfectly stationary, it's moving around. And they are really this common process of how do you treat the noise as a frequency noise power spectral density. So I'm a big believer of looking at everything through the distribution of a Fourier frequency.
I see. So it's like it depends how you look at that curve.
Yeah.
So one is like the central frequency moves.
Yeah.
And the other one is
It really basically tells you whether you're dominated by the frequency noise at a higher Fourier frequency or you're dominated by a frequency noise at a lower Fourier frequency. And one gives you more sort of Lorentzian type of line width if you're dominated by high frequency fluctuation. The other one is more looking like a Gaussian line width, dominated by the low frequency drift and so on. And that this can all be very mathematically described and very rigorously defined.
And so for atomic clocks, for optical atomic clocks, you need stable lasers, and you need also atoms which are cool down and have the finest kind of transitions. So how do you put it together into a clock, and then maybe moving towards like what is like the state of the art in optical atomic clocks these days?
Yeah, I mean, putting them together just means like that's why we were emphasizing trying to achieve long coherence on either side. You need to, if the laser is jittery all the time, then you wouldn't be able to see this pristine quantum coherence the atom offers you. So you're not taking best advantage of it. On the other hand, if the atom is wobbly, if the atom is not well controlled, then that's a not good reference to begin with. And in fact, to be honest, our laser downstairs, the silicon cavity laser, that stability is better than most. Don't want to be boastful or brag, but it's actually more stable than most other people's atomic standards. Just because this is exactly the statement that you have to do good job on both sides, and because of that, the atomic side, there's a tremendous amount of science and engineering got in. I think people start to become really good at laser cooling in the late 80s. So this felt like my generation, where I was a graduate student in the 90s, mid 90s. We actually learned a lot from the early pioneers of laser spectroscopy, like Latikov, Shabatayev on the Soviet Union side. On this side, Jan Hals and Shallow, Shallow at Stanford, Ted Hinch, and so on, these heroes. And the field moved into laser cooling and trapping, pioneered by people like Bill Phillips. I understand he's one of your podcaster, Steve Chu, Claude Continuigi, and I'm only naming a few representative names. Of course, the whole field is pushing forward by many really pioneering workers in that field. But that gave us, by the late 90s, we mentioned Eric Cornell, Carl Weinman, Wolfgang Ketterle, made a Bose-Einstein condensate. And I must say also another of my dear colleague, Debbie Jing, who was the first to create degenerate Fermi gas. Those technologies becoming now easily accessible to us. And so it's felt this incredible opportunity where the atoms now can be, in some sense, once they cool down, the entropy of the particle becomes really low. So you can start to dream about putting atoms one by one in optical lattices, right? Like there's a grids of the geometry you can create by interfering laser beams. And if the atoms has such low energy now, and such a low entropy, you can just put them one by one, like almost like a pattern of eggs sitting in the egg carton from the supermarket. And this is the power that I realized when I was a postdoc with Jeff Kimball. He at the time wanted to work with a single atom, but I came from JILA where we have lots of molecules. When I came back here to be a faculty member in late '99, this was exactly the direction I thought I'm going to push. To put many atoms together to build an atomic clock that potentially can reap the benefits of this long coherence time, but large number of atoms. And in saying this, I should have mentioned another local hero here in Boulder, which is Dave Wineland. Dave Wineland's group has been pushing already in the late 90s, where they have a single trapped ion, one ion was having a better clock time than cesium atom already in the late 90s. And it just feel like maybe we are just scratching the surface. What if we have millions of these atoms all working together, doing something similar to what Dave Wineland was able to do with single ion? Then you must be able to do better than Dave by a factor of square root of a million, which is 1,000. And so at the time it was like unthinkable. Like Dave is already at this absolute best. Can we do 1,000 times better? And it turns out these kind of a vision are not being realized.
I see. Maybe it's like going towards one of your, I would say, the most recognized accomplishments, that the PRL paper of, was it 2018, about the optical atomic clock, where you use the 3D lattice to...
Oh, it's a science paper.
Oh, science paper. Okay.
Yeah.
Maybe I read like several papers.
Yeah, there's several papers, yes.
I see.
Okay, that's the Fermi degeneracy clock.
Where it was like hitting towards 10 to minus 19, or what was...
Yeah, 10 to minus. Yeah, so at the time, I would say there's a series of papers that was around 2014 when there was a paper written by Ben Bloom. He was the first author that showed that we can characterize clocks at the 10 to minus 18 level, 7 times 10 to minus 18. And that at the time, that set a record of what is the accuracy can be coming. I mean, that's really the first clock that went into the 18 digits. Before then, it was all 17 digits. Ben Bloom, by the way, is the CEO that he later opened a company called Atom Computing for quantum information. After him, there was Travis Nicholson paper that showed that we can characterize strontium, all the systematics at a few parts 10 to the 18 level, so a little bit better. And then we wanted to push on is how do we scale up the system? So in order to get to 10 to the minus 18, it took many seconds to average. If you have your stability, say, at 10 to the minus 15 at 1 second, in order to get to 10 to the minus 18, you need to average 10 to the 3 times squared. And so that's a 10 to the 6 seconds. That's a lot of time, millisecond, right? And so that's a several days, 10 days, almost a month. And that's not practical. In normally, when you say, I want to smoke out some systematics, the ideal time is a few hours. That's just because of the human attention span. But ideally, you want to be a day.
It's patient limited.
Yeah, patient limited. But it's really true. In all physical science, it's always true. Like you work hard until you get to say, oh yeah, of a few hours, I can find out what's wrong. You don't wait for a few months to find out what's wrong, because oftentimes then you don't converge. And that's maybe just associated with our particular species. So it's interesting, right? No, if we can scale up our system from 10 to the minus 15 at a second stability to 10 to the minus 18 at a 1 second stability. This is what we just recently achieved. Then the systematics can be, and the averaging time is a square of the stability. So if you can reduce stability or precision by factor of measurement imprecision by factor of 10, you gain by factor of 100 in your waiting time. So that's a big deal. And so over that time, we started to develop three-dimensional optical lattice where we put a degenerate Fermi gas into a three-dimensional optical lattice. All of that is a scalability. I'm a big believer in scalability.
So how well can you populate the three-dimensional lattice? Is it so you have basically like three
interfering beams?
Yeah,
3 counterpropagating beams. We were able to get it into such a low temperature that we can almost have every single cell filled by one and only one atom. So really, essentially, no entropy.
So it's the nature of the strontium isotope you work with, so it has this
the fermionic
nature.
Yes, that's
and
correct.
Then cooling it down to
the degeneracy, the Fermi degeneracy.
Fermi degeneracy, I see.
Yeah. What does Fermi degeneracy mean? Just means that these atoms are so cold that they have to go to the absolute bottom of whatever the harmonic trap you build for them. But if somebody is already at the bottom, because I'm a fermion, I cannot go to the same place that somebody already occupied the seat. So I'm going to have to take one row up. And then the next fermion coming in say, oh, you already have 2 people there. I will take another seat up. And that's what the Fermi seat is. It's called a Fermi seat. And the highest level of Fermi seat is where they will be defined as a Fermi energy. And so when we say quantum degeneracy, it just means that thermal fluctuations are far below this Fermi energy of your system.
And then I remember there was yet another important detail that you adjust the trapping frequency. You call it like magic frequency, magic wavelength.
Okay. Yeah. So that's actually we haven't touched on. I'm glad you raised this point. So remember that. Let's go back to dial clock back to 1999 when I was starting here. Dave Wineland was our inspiration. Right? Dave has one trapped ion. If you say, I want to do Dave Wineland, but build 1 million trapped ions, that's a lot of a resource to build. But if you say, I want to put 1 million ions in Dave's ion trap, that won't work because ions interact very strongly with the Coulomb force. So then seeming like the idea is to build 1 million copies with neutral atoms, and neutral atoms don't interact as strongly. But how do you do that when you have a million atoms in there, and how do you have them very orderly occupy one cell by themselves, not interacting with the rest? That really took a long time. That's the sort of the vision to scale things up, but it required these atoms to be cooled down to very, very low temperatures, deeply into the quantum degeneracy, and have their interaction be very precisely controlled. Doing all that, you still have to worry about one thing, which is in Dave's trapped ion, his trap is working on the fact that the atomic species, is charged, and so you can trap them without having influence of what's the separation of internal energy levels. With neutral atoms, we do not have this charge that we can hold on to, so we have to build optical traps where you are actually deforming the energy levels of neutral atoms. And the very fact that optical tweezer is a very easy way to visualize this. I focus my laser beam to very, very small, tiny spot, and I'm creating AC stock shift of these atoms. And this AC stock shift will be spatially inhomogeneous. And that's the reason why you can build optical trap, right? It's a spatially inhomogeneous AC stock shift.
Like a potential well.
It's like a potential well. And so this optical potential well you create, you must worry how that's going to influence of your clock, because the optical potential well is created out of the internal structure. That's fundamentally different from ion trap. They're just using Lorentz force of charged ion. So this is the biggest worry. Like if I build trapped neutral systems and I build this optical trapping potential, but what about the two clock states? If they had a different trapping potential, then obviously the frequency measurement you're making is totally wrong. And this often is the case when you build a laser trap, or trapping atoms, and you go to the excited state, ground state, the two potentials are completely different. And so this is what people call AC stock shift. Right?
How much they usually
shift.
would
It can range from tens of kilohertz to the entire trap depth, or megahertz, all the way down to few hertz. None of them is good enough. No, remember the goal is to go to below millihertz or microhertz. Yeah. So this really came up with. So this is actually quite an important concept, so-called magic wavelengths, which is, can I find a particular laser wavelength where I can create this trapping potential, but this trapping potential is identical for the ground state and excited clock state. If it is true, then it doesn't matter anymore how the atom is moving inside the trapping potential. The two potentials matched. So the clock states, just like in ion trap, you can separate internal degrees of freedom from external degrees of freedom. And suddenly you can do all these things that you wanted to do. And that's always a key in atomic physics. When something you don't understand is your systematic. But once you understood it, it can turn into a tool that you can manipulate internal degrees of freedom, external degrees of freedom at a free sort of level. And so this concept was actually coming from, again, credit to Jeff Kimball. I was his postdoc at the time, and we want to create a cavity QED system where external trapping potential does not influence the dynamics of the atomic evolution when we go from ground to excited state. So at the time, we were already coming up with the idea of the magic wavelength trapping in that consideration. And so when I was coming back to Boulder, to JILA, to take up a faculty position, I'm bringing back this magic wavelength idea. And fortunately here at the time, there was a theorist called Chris Green, who later moved to Purdue. And Chris and I immediately connected in 2000, actually have a bunch of his calculations. He sent to me saying, hey, Jun, here's a strontium. Here's your favorite atom, strontium. And I have done these calculations for you. If you ground state, excited state, if you want to use these two levels to be your clock, that's the wavelengths you want to use. And this idea was independently pursued by Professor Hidetoshi Katori at University of Tokyo. And in fact, he was the first even to really put that idea together with a single S0 or triple P0 transition. While at the time at JILA, we were thinking about single S0 to triple P2. But it's the same idea of being able to really create many parallel copies of optical traps. So many atoms can be used while we do not have to worry about this deleterious effect of optical trapping potential itself. So we want to take advantage of optical trapping because we would want atoms to be confined in a particular location, not moving around. But on the other hand, we do not want to suffer from the consequences of the trapping.
So is this the magical wavelength? Is it special only for strontium,
No.
or it's like for a group of atoms, or
It
any atom?
turns out any atom that you have. So once that idea is realized, then people of course realize, yeah, you can use for any the. If you only have two levels, you can never create a magical wavelength. If you have only two levels, because whenever you have photons interacting with two-level system, one level is pushed down, one level is pushed up. But we know in atoms, it's not two-level system. It's about many other levels. So you can always find a wavelength, and where you can say, I want to push both states down, or want to push both states up, and turns out to be universal. Of course, there can be luckiness or unluckiness where maybe the wavelength that was working perfectly for you, it's a little bit too close to resonance, so it can cause spontaneous emission, scattering, and so on. But almost all technically relevant atoms these days people are working on, they can always find the magic wavelengths to work for them.
I see. So also, since we have like another developing tools these days, like let's say machine learning, like AI,
Yeah.
do you see how this tool can be integrated into your system and push forward the?
I think machine learning and AI can help make the system much more robust. I actually think the design principle of atomic clock in principle are here, but machine learning can help optimize it and can maybe search for what kind of a best sequence, how many, there's still many sort of directions to push. Like, for example, these days we're talking about, can we make a continuous atom source? I don't want to just realize atoms sitting in the magic wavelength trap and just kind of a one time at a shot. But I would rather make it a more continuous flow of atoms coming in, and I can utilize this all the time. Like we discussed about making the best laser. In some sense, maybe in the future the boundary is blurred between making the best laser, but also making the best clock. And this kind of a merging of how do you do quantum resources. Maybe in the future also we want to use entangled states. We haven't talked about this. I do think this days will be coming where entanglement generation will be robust. And again, we also are pursuing such an experiment where we are generating spin squeezed state. And we can use the spin squeezed state to pushing on below the so-called standard quantum limit, meaning entanglement is giving us some benefits. But it's not yet pushing the absolute best. The absolute best system, the clock downstairs is still atoms that do not need to necessarily use entanglement, just because when you generate entanglement, it takes time to do it. It takes other resources to do it. But the optimization process, I do think will be coming, where I want to use a continuous source of atoms, million atoms per second flowing through my system.
So it's like a conveyor, like
it's a conveyor belt, and they are all
that.
trapped, and they are all quantum state completely under control. It's not like old-fashioned atomic beam where it's a thermal source. No, every state is quantum controlled. Maybe entanglement is actually being built in, just like a quantum computer. And I do think quantum science as a whole is really moving forward in that way. Like quantum information allow me to process the state excitation and the state manipulation in an optimized way, will teach me how to build my best atomic clock is in fact using entangled states, corrected errors, and do this continuously. And from that point of view, I think there's a lot of optimization to be had.
Is there like an intuition? So like from your papers and talks, you mentioned that the phase noise in the clocks, it's like proportional to number of atoms. It's either like a square root of n, or if they're entangled, it's proportional to
1 over n. Yeah.
1 over n. Where does it come from? Like why entanglement helps to get a better dependence on the number of atoms?
So in some sense, you can think that way. Like suppose I prepare 10 atoms, n equals to 10, just so that it's easy to discuss. If I got 10 atoms, each one of those 10 atoms are independent of each other. So each atom you measure, there's uncertainty due to Heisenberg uncertainty principle. You can think of this as fictitious angular momentum as a non-permutation between Jx, Jy, and Jz from that language, or you can from the measurement postulate whenever you have a coherent superposition of two states, and when you make a measurement, you never know which state is going to come out, right? This is the fundamental indeterminism in quantum. And that gives rise to each atom when you make a measurement, there's an uncertainty limited by that. Now you make 10 copies of such measurements. You have a 10 times more signal, but you also have 10 times more noise. The noise scales as square root of the 10 measurements. So that's where the square root of n come from.
It's like statistics noise.
Yeah, it's a white noise. You make more measurements, the noise go down as a square root of the sample. So signal scales with n, noise scales with square root of n. The signal to noise ratio squares with n over square root of n. That's why the square root of n comes. Now, if in the entanglement, you can think of the following picture. When I have 10 atoms actually entangled, in the best case scenario, is that in the entanglement means your fluctuation will dictate mine, or our fluctuation are adjoined. So even though I have 10 atoms, there's only really one copy of fluctuation because they are entangled. So from that perspective, you have 10 copies of signal, you only have one copy of noise.
It sounds like close to this kind of redundant or quantum error correction approaches, or it's something...
This is different. This is just telling you that because of the entanglement, I mean, in some sense, quantum mechanics, you can think of the most deeply profound aspect of quantum mechanics is this Heisenberg uncertainty principle. The wave function and so on, in some ways, in classical physics, we have wave functions, right? So interference and so on. I think the most intriguing aspect of quantum mechanics that people always find puzzling, one is superposition. They can at two different locations at the same time. And that associated with that is that when you make a measurement, there's always the state collapsing. However you want to interpret the quantum mechanics, there's nevertheless the practical consequence is the noise, and that noise is the most fundamental aspect of quantum, and no classical physics has this indeterminism. And so in some sense, it's kind of funny that I always talk about this way. In clocks, we use quantum certainty principle where energy states are eigenstates of Hamiltonian. So therefore, it's absolutely certain what energy level you're going to measure. But there's uncertainty because you prepare a superposition between two states. And when you make a measurement, there's uncertainty built in. Quantum gives this yin and yang, this intrinsically conflict, but it's beautiful combination, right? And what is entanglement doing to us is, well, if I can have two different quantum particles to be completely entangled, meaning they're intrinsically fluctuating, and that fluctuation is not something you can control. But the two particles as a whole, their fluctuation is completely correlated, well beyond what classical correlation can describe. And this quantum entanglement, quantum correlation, makes the quantum fluctuation to be only one copy, even though you have two different independent particles. And that's a very key aspect of quantum mechanics. Also lies in how you process information. Whether it's a quantum computer is using exactly the same protocol, quantum communication is using exactly the same protocol. It's this correlated noise. That's the aspect that is no counterpart in classical physics. So it's like really intriguing that quantum gives you this inescapable noise, but somehow you can make entanglement such that, let's make the inescapable noise to be as small as possible by entangling all the particles. Or when you entangle all the particles, maybe you can share information well beyond when anybody who break them apart, you have two independent noise process. Therefore, they can no longer hear what they are trying to communicate. between entangled
So
particles.
those like correlations, they make it more prone to noise and
Yeah, exactly.
I would say
Not less
protect from the noise.
against
less
noise.
prone.
Yeah,
I see.
yeah. So that aspect is really important, and I think this is really the fundamental key that we are starting to try to take advantage of in the second quantum revolution, and that's why whether it's quantum computing, quantum information processing, quantum communication, or quantum metrology, as we are discussing today, it's the same thing. It's the same deal that we are trying to take advantage of. So to me, this quantum scaling up, on one hand, is to use as many particles as possible in the pristine quantum states. That gives you a square root of n scaling. And in the future, you put it in quantum entanglement, that's 1 over n scaling. That's even more powerful. But regardless, you need more and more particles. You need to make n large.
Yeah, touching base on like quantum computing. So it seems like it's kind of one of the branches from optical atomic clocks. I would say, like, in general, atomic clocks. So what's your view on kind of the current things which happen with like quantum computing? Like,
Yeah, I think in on many ways the quantum metrology, like atomic clock, provides a lot of a technology for quantum computer. The qubit has to be rotated very precisely, and in fact, you want to do so-called deep circuits. You want to rotate the qubits many times. You want to have hugely incoherent sort of evolution. The coherence time must be much longer than the individual manipulation time or individual evolution time or gate entanglement time, so they can do multiple calculation steps, which is so-called deep circuits. And so on one hand, the metrology, quantum metrology, really provides underpinning technology platforms for quantum computers.
so it's like improving fidelities of the gates
Yeah.
because it's all noise dependent.
For example, yeah, and all the tools they're developing, the lasers. We're talking about lasers. If you want to use optical qubits, laser is one of the key fundamental pieces of technology. And so that's that. But on the other hand, there's also a very deep connection when you have, I can generate GHZ states, I can do error corrections, I can do, quantum algorithm on the fly. I do think this will come back and then do optimization on the clocks. And so in my mind, this field is going to, quantum metrology also has this connection to fundamental physics. So as we briefly mentioned, as the clock gets better and better, you can probe the interface between quantum and gravitational physics. You can use this to search for unknown physics that we know that the standard model is not complete. And so from that perspective, I find it super exciting where quantum information science will make clock better just because of the technology flows both ways, but also intellectual connection. Like how do you make a better measurements, make a better protocols, take a resource of a lot of quantum entanglement, correct all the mistakes you might make along the way, the systematic errors and so on. And that will make you, I think, continue to make a huge progress. Over the past 20 years, we improved our clock by 5 orders of magnitude. And this will still continue to improve in my mind. And it will be connected to the overall advancement of the entire field of quantum science. And then connects to fundamental science. I think that's where potentially we'll have discoveries in the coming decades.
So do you see like the fundamental limits or walls which would
Yeah.
what is the ultimate like sensitivity you can achieve?
I don't see it. That's what I feel like. That's why it's, by the time you see it, you will see new physics. That's why I think it's so exciting. Like you will see it. You will see fluctuations. You will see, if nothing else, the universe is not a quiet place. There's gravitational waves. People are trying to find a way to see it. And when your clock is good enough, you will see those gravitational waves, right? And that will be the noise of your background. So that's why I feel there's no losing cause here. You develop the technology, you keep moving forward. And if one day people say, no, you can no longer make time measurement better, you have come upon some interesting physics. Maybe quantum gravity finally will say, yeah, time is no longer continuous, it's all discrete. But that's many orders of magnitude away. But I think along the way you will find a lot of other interesting physics.
Yeah, yet another interesting research direction you're doing is so one is like atoms,
Yeah.
electron transitions. Another way is going deeper into the nucleus and
Yes, that's
leveraging the
indeed.
nucleus transitions.
Yeah. And I think from that perspective, along the same line of fundamental physics connection, well, if we can, atomic physics became totally different when laser was invented, when people start to shine laser onto atoms and start to see the sharp features of atomic structure and understanding them, and then turn this into a technological platform we are talking about today, atomic clocks or quantum computers. Nucleus have not yet gone through this renaissance, like man-made field can open up a nuclear shell and understand what's going on inside, right? The nuclear model, in fact, is very imprecise, partly because it's very difficult. It's got a many-body physics going on, but partly because there's no guideline, no guidance from precision metrology to like, okay, let me go in and open this nuclear shell and understand what are the nuclear energy levels. Once you can start to do that, I'm sure the theory will match up with the experimental inferences. So from that perspective, I find it super exciting to be able to use lasers to excite nuclear transitions directly, because you can now start to check whether that liquid model people talk about, oh, here you got a nuclear quadrupole moment, nuclear octupole moments, and now you can poke it and this little liquid start to vibrate, and you can say what vibration frequency that is, and so on. So from that perspective, I do think, and inside nuclear physics, you have a QCD and a QED physics. And if you start to being able to explore the energy levels, that will allow you to check QCD physics, just like we have done so well with the QED, with atom and lasers. And but on the practical side, the nuclear clock might offer this opportunity where atom-atom interaction is relatively strong because you're using electrons, and electron can feel the electromagnetic fields, and they can more easily be influenced by electromagnetic fields. They can interact with each other. What nucleus, the excitation is hidden inside the nucleus, protected by the shells of electrons. They will still be sensitive to magnetic field and electrical fields because of nucleus has moments, and they will be responding to those external fields, but it was much less sensitivity. And you can imagine you can have a lot of nuclei be engineered to put together. So talking about scaling, this is what I was talking about now. Maybe you can scale to a very macroscopic number of quantum absorber like nuclei. What if we have a crystal with 1 Avogadro constant worth of nuclei? So now, instead of talking about million atoms or 1,000 atoms or one atom, I'm talking about 10 to the 23 atoms, 10 to the 23 nuclei. And that scaling feels very, very promising and very exciting. We are nowhere close to that, but we are like scratching little surface here, just trying to see what are the first few steps that we are taking.
Do we have like the tools to touch those
Yeah, so in order to like open up a
transitions in
lot of nuclei, I think there will be a lot more development on lasers to go to the extreme short wavelengths. What we were lucky enough that we have been doing this so-called XUV comb. Like this goes back to the frequency comb. When we get the frequency comb going, was all indivisible. But we started to generate mid-infrared. That's a little bit easier because you put a two frequency comb beat against each other. You can generate different frequency combs and so on. But into extreme ultraviolet, it actually turns out to be much harder. And we rely on some of the technology called attosecond physics, and to generate this incredible pulse that's so nonlinear, extremely nonlinear, to produce many, many harmonics, odd harmonics. And we do this in a way that we can make the phase coherent at high repetition frequency. So we were among the very first group, together with Ted Henschel's group, that generated the world's first frequency combs in extreme ultraviolet back in 2005. But you can see it took us 19, 20 years to make this frequency comb to be good enough to actually shine onto nucleus and do spectroscopy with high resolution. And so this is amazing. But I think this is only one example. If we can push that technology a little further into soft X-rays, then potentially the entire nuclear field will be opened up. So I do think there's a lot more work can be done in that area. In our group right now, because we have got this initial door opening of the high resolution spectroscopy of thorium-229, we'll be staying here for a little while to kind of see how deeply we go into that field.
Yeah. And on the side of the lasers, so you said you mentioned like extreme UV or like also this VUV, deep UV lasers.
Yeah.
How we do we have those tools like available essentially?
Yeah, so we
Like,
in our lab we can push this to thorium transition. By the way, is sitting at a 148 nanometer, and you typically would call that as a vacuum ultraviolet. A deep UV is in the 200, 300 nanometer region, but we have demonstrated that we can push such wavelengths down to 50 nanometer. That's in the extreme ultraviolet, below 100 nanometer. But we stopped there. In principle, you want to keep pushing down. Maybe 14 nanometer, 10 nanometer, maybe one couple nanometers. There are experiments, large scale experiments, advanced light sources in Stanford Linear Accelerator and other places where people can get into the X-ray region. But those are light sources which are not having high spectral resolution. So that remains to be a challenge. How will we be able to generate such light sources in below, say, 50 nanometer spectral region that can have a high spectral resolution?
Are there any like theoretical predictions? Let's say if we compare optical atomic clocks versus the nuclear clocks. What's the like the in terms of accuracy and precision? What would be the advantage here?
So the nuclear clock, just because it's less sensitive to the external environment. For example, black body radiation is something I worry about for our strontium optical atomic clock. For nuclear clock, you don't have to worry about it. When I say don't have to worry about it, meaning at 10^-20 level, you don't have to worry about it. So there's obvious advantage there. The nuclear clock right now suffers from the fact that the field is just at the very beginning stage. There's no quantum state engineering. Atomic physics, after all, is very sophisticated at the moment. So that's interesting. The kind of having two tracks and see how these two fields and actually compete with each other. It will be interesting for us to watch. And then I think ultimately nuclear clock should win, ultimately. But that's only when we start to be able to pi over 2 pi pulses, flip nuclear spins just like it's a qubit, and all these quantum controls things start to come into play a role. We can understand all the line with broadening, line with shifting mechanism in the crystals. That's going to just take a while to really for us to move the field forward. But you mentioned this comparison, and in fact, that's already happening. So we saw the nuclear transition last year with this high resolution excitation. And so we have been keeping frequency record already for many months. And talking to some of the particle physicists, they got super excited by wanting to have this record of frequency because we are comparing our nuclear transition against the strontium transition. Strontium transition is mostly determined by QED physics. Nuclear transition has both QED, QCD in there. And suppose you say there's some dark matter, ultralight dark matter that's coming in an unknown way, interacting with some of the matter that we don't know, because that's a very unsatisfying status of physics where we are calling it dark matter because we don't know what's going on. But if there is one signature that's going to show up, some people talk about fundamental constants may not be a constant, but it can couple to this unknown force of dark matter. Well, comparing two atomic clock is less favorable than if you're comparing atomic clock against nuclear clock. Those are two different, physics origins. And the nuclear clock will amplify any of those effects by a fairly large factor. So if you want to see something that's weird is going to happen, nuclear clock will be great to have.
Or even build like maybe a distributed network of both
exactly.
nuclear and atomic clocks.
Yeah.
One of our favorite questions is, so if you would have unlimited resources, is there maybe any other projects you would come up with or start doing?
I think if I have a lot of resources, I would definitely like to pursue on both atomic nuclear clock how we can build a quantum system to, can I have billions of atoms flying through my well-engineered quantum state trap uh, at a scale of billions of atoms per second or even more, just being able to scale up the performance of the clock to such a level where I can start to be able to see these quantum decoherence, quantum effects induced by gravity. Can I see the space-time curvature? We know Earth is a weak field, but actually, in fact, you also know the field has gradient, so meaning the field is not linear. It's already got a space-time curvature. I would love just keep digging on that to see the connection between quantum and gravitational physics, partly because that's a field that's being not connected. And also on the nuclear side, we would love to have more resources where you can have lasers, develop lasers. If nothing else, I would love to upgrade my lasers by another factor of 1,000,000 in power. So then I can really start to manipulate nuclear spins if they're coherent qubits. Maybe in the future, the quantum computer could be coming out of the nuclear qubits. Why not? If you got a 10 to the 23 and you can control them and you can understand all dephasing, decoherence, and the information can be stored. We know that in our lab, we can see the nuclear state live there for 20 minutes when you go to the excited state. So it's a quantum state engineering is waiting for this opportunity to be developed there. So these are the fields I would say I kind of know what kind of tools that's needed. Better coherence time on the optics side, better state preparation with larger and larger number of atoms and nuclei, and pushing them together.
So it's just like getting enough of funding for building those like components to the experiments.
There's of course a healthy level of balance. Obviously, I wouldn't be able to handle lots of funding just because ultimately every day you're working on one experiment, right? And you're working with 3 or 4 students on one particular experiment. But I think what will for the field, for the community, would it be healthy to have more people working on these different technology developments and people can share this in an open way.
Okay. Maybe also anything else missed in this conversation what you would like to add?
And I think we covered a lot. I'm pretty happy.
There was another interesting fact from your biography that you were born at almost like at the beginning of the social revolution in China. Did it have any impacts?
67.
Yes.
Yeah.
Did it have any impacts on your
cultural revolution?
On your life, on your professional career, like how you see the how do you approach the problems?
Yeah, actually, it's kind of interesting that I was born in 67. The Cultural Revolution was from 66 to 76. That was the time that I'll say turmoil, the past, and I think there was a lot of struggling. Chairman Mao probably wanted to have more power to himself, or I don't know. He's always, whenever there's a technocrats, people who are managing economy and so on, they're coming from a more professional point of view. Maybe Chairman Mao felt like, I don't want to listen to them. I'm just going down all the way to the mass, and then talks to the mass. And then whenever farmers and workers decide what they want, he will use that to say, okay, you guys should go away. This is what my mass wants. And so it's an interesting period. Typically the Chinese society is more sort of you take education, you move up the ladder, and the governing elites. I guess most of the society are like that, but that was an interesting period. I did not really experience that much because I was obviously when you were born, you don't know. Both my parents were college educated, and my mother is a scientist. My father is a business person. They were both college educated, and they nevertheless always emphasized education is very important. So in my first formative years by the time I was 10 years old, I do remember, Cultural Revolution ended, and people experienced this incredible burst of suddenly freedom. And I did witness this interesting period for 2 or 3 years where the country had, like, our household is considered medium, fairly well off kind of a family. But nevertheless, we had no refrigerator, no car, no color TV. All of that changed in 2 or 3 years.
Did you grow up in Shanghai?
I actually grew up in a city south of Shanghai.
South of Shanghai.
Yeah, I was born in Shanghai, but then my parents lived in a city about 200 kilometers south of Shanghai. Wealthy place, very well off in terms of agriculture and wine and all these kind of seafoods, but it was not a modern society. I do think that had an impact on me, that if you can let people go free, if you can just, everybody, please, use your best creativity, use your best natured intention of making life better for everybody else, things can change really fast. It was 2 or 3 years later, every family had a big color TV, every family had a refrigerator. It all happened within my middle school. It's actually hard to imagine. Like, being American, you're born into,
you don't appreciate it.
You don't
have it.
In my generation of Americans, already TV happened before their parents were teenagers, and so you don't see that. But China's transformation was very, in some sense, spectacularly steep. I think it actually shows where people's it was bubbling just below the surface. People want to work, but system was clamping down. And when this got bursted, how can society change so fast? In 20 years, it went from, I remember when I was going to see my grandmother in Shanghai. I was living 300 kilometers. It go on a train. The train has to stop every step. It's a 6-hour journey. It's like a 1 day, right? And 10 years ago, when I went back to when I was on the bullet train. 40 minutes later, it's done. It's amazing, like the transformation. So I think that buried in me this notion of, if you do good science, good technology, you can make people's life better. If as long as we can pursue this with intellectual freedom and with collaboration with people, opening the ideas to everyone, everybody benefits from kind of a way. Hopefully, we can continue along this path.
Yeah. Okay, I think that's a good ending for our podcast.
Okay.
Thank you.
No, thank you very much.